All right, so looking at this has some of the definitions we need to know. For e to the x, our Taylor polynomial is given by this. Remember, this is only if it's centered at 0. Sine x is odd, so its Taylor polynomial looks like this, and here's its general term. Remember, if we want it to be odd, 2n makes something even, so 2n plus 1 is going to make something odd. Cosine is the evens. This right here is a geometric build, a over 1 minus r. So a is your first term, and you multiply by r to get the next term. Now, things that we already kind of had memorized, if there's a factorial on bottom and nowhere else, it has an infinite radius of convergence. If it's geometric, we know for geometric that only the absolute value of r has to be less than 1 for it to converge. So for this one, we knew that r was equal to minus x. So the absolute value of x is going to be less than 1. So this is between -1 and 1. The other thing we know about geometric is you do not have to check your endpoints. Those are your known polynomials. These three I consider my known polynomials. I consider this my geometric build. And right here is our definition. So we have the Maclaurin polynomial. Maclaurin just means it's centered at 0. And this is your Taylor polynomial, meaning it's centered anywhere. So looking at this first one, we want to find e to the 2x. So remember, we can use known polynomials. We can use the fact that it's a geometric or the definition. But looking at this, it's very close. It's just a manipulation of the Taylor polynomial of e to the x. It wants the first 4 terms and the general term. There's your first 4 terms, your general term. So now to get to e to the 2x, everywhere you see an x, it's now going to become 2x. So e to the 2x is then equal to, let me move that up so I can simplify it below, 1 plus 2x plus 2x quantity squared over 2 factorial plus 2x quantity cubed over 3 factorial, and then our general term, and this goes on forever. Now, if this was the Taylor polynomial in part A, I would just leave that alone. But do notice that if you're going to need to use it later, then you want to go ahead and simplify this. So this would be 1 plus 2x plus 2 squared x squared over 2 factorial plus 2 cubed x cubed over 3 factorial and 2 to the n x to the n over n factorial. And again, like I said before, is make sure you have consistencies. You see they're all positive. I've got squared, squared 2 factorial, cube, cube 3 factorial. So you should see lots of consistencies. It's an easy way or a quick way for us to see if there's any, just really big errors. So same thing, we want the first 4 terms, 3 non-zero terms and the general term for this. So looking at that, we're again going to start with a Taylor polynomial for cosine x. Cosine x is the evens, so 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And then our general term would be -1 to the n, x to the 2n over 2n quantity factorial. So now what we need to do is multiply everything over here by x squared, which means we're going to multiply everything on this by x squared. Now when we multiply by x squared, it's going to bring the power up by 2. Everything else is remaining the same. So multiplying it by 2, you're going to have 2n plus 2 all over 2n factorial. 3. Given this following series, determine what f of -3x would be, 3x squared. So let's see, f of x is equal to x plus x squared plus x cubed over 3 minus x to the 5th over 30. And if we want this, that means x is now going to become -3x squared. So this will be -3x squared plus -3x squared squared plus -3 3x squared cubed minus negative 3x squared to the fifth. And again, we're going to simplify this, but we can see we start with negative 3x squared. That does not help us at all. The next one is going to leave us with a positive 9x to the fourth. So we know it's not A, we know it's not B, we know it's not C, so it has to be D. Let's go ahead and check the next term just to make sure we've got everything correct here. So this would be minus 27x to the sixth over 3, and 27 divided by 3 is in fact that negative 9 you got right there. 4. So they want us to find the derivative of this. So let's see. On the AP test, they never ask you to take the derivative when the summation's there. So let's just take the derivative without the summation and see what happens, and then see if we can match it. So remember, when you take a derivative, you're really taking the derivative only on the x power, because this is your only variable. So when I take a derivative, this power is going to come down in front. So 5 times n, 2x minus 3, subtract 1 from the power, divided by n factorial. So now we can simplify a little bit. F prime is going to be the same thing as 5 times 2x minus 3, n minus 1, all over n minus 1 factorial. And then we have to multiply by 2, the chain rule. So that's going to give us 10 times 2x minus 3 to the n minus 1 over n minus 1 factorial. Sorry, at the first point I forgot my chain rule. I was going to rewind, but I just forgot. So going up here, I believe this is C. Now, if we had these, and it looked very similar to this, and one started at 0 and one started at 1, I would go through and look at the original polynomial. So my original polynomial starts at 0, so we'd have 5, all that to the 0th power, all over 0 factorial. So I know my first term is 5 with n is equal to 0. If I take my derivative, my 0th term went away, and we're now starting at the first term. All right, looking at number 5, it says a Taylor series for g of x about x equals negative 2 is given by that. We know that it's centered at negative 2 because here you can see x minus c. So x minus a negative 2. So they want us to find g prime. G prime would just be the derivative. So the constant goes away. So the first one would be 4. And then here you're going to do power rule, 8 times x plus 2. And the next one would be 8 times x plus 2 squared. And then we go all the way down to, we're going to bring that n out in front. So we're going to have 2 to the n plus 1 times n divided by n factorial over x plus 2 to the n minus 1. Make sure you do exactly what they said. The first 3 non-zero terms, 1, 2, 3, and the general term. Of course, you can simplify this general term a little bit. You can say that this is, in fact, 2n plus 1 over n minus 1 factorial, x plus 2 to the n minus 1. All right, so next piece, we have find the radius of convergence. So the shortcut for this is notice that there's no factorial. Remember, if you have something with a factorial on top and nowhere else, the radius of convergence is 0. If we have a factorial on the bottom, that means it's decreasing extremely fast, which means the radius of convergence is going to be infinite. Otherwise, if there is no factorial, you look for the geometric piece, and this right here tells you the radius of convergence. So right here, we can see this is our radius of convergence. So we see that x plus 3 has got to be less than 2. So our radius of convergence is 2. Now, if that was a multiple choice, that's enough to show. We don't have to show anything on a multiple choice. But if this was a free response, this is worth 3 points, and you have to use the ratio test. The only time you do not use the ratio test to show the radius of convergence or to find the radius of convergence is if it's geometric. Because geometric, you can just go to the little ratio has got to be less than 1, and that'll find your big radius. So for the ratio test, you do the limit as n goes to infinity of an plus 1 over an. So this will be the limit as n goes to infinity, x plus 3 to the n plus 1 all over n plus 1 times 2 to the n plus 1 multiplied by the reciprocals. Simplify everything you can, cancel. So we have an extra x plus 3 on top. We have an extra 2 on the bottom. And at this point, we always check to make sure the degrees are equal. The degrees should be equal unless there was a factorial. So this is equal to the ratio of the leading coefficients. Now remember, for the ratio test to work, this needs to be less than 1. And our goal for the ratio test is always to get x minus c less than r. So for us, x plus 3 has got to be less than 2. So that tells us the radius of convergence is 2. The Taylor series for f about x equals 2 is given by this. Find f of 1. So they want us to know exactly what f of 1 is. It doesn't say approximate. It says find or then. It is not an approximate, which means we should be able to do it exactly. So the first thing I'm going to do is plug in 1. So this would be 3 minus, because you do 1 minus 2, so it'd be a negative. The next one would be 1 minus a negative 2, so negative 2 squared, which would be positive. And the next one's going to be negative. What type of series is this? Well, if we're asked to find the exact value, it's either got to be geometric or something we recognize. And looking at this, this definitely is geometric. A is equal to R. A is equal to 3. That is the first term. R is what you multiply to get to the next term. So to get to the first term, to get to the next term, I'm going to multiply by negative 1/4. And remember, this sum for a geometric series is a over 1 minus r. This is a convergent geometric series because, first of all, it's geometric. It has a common ratio, and the radius is the common ratio is less than 1. So that implies that it's geometric converges. So a is 3 over 1 minus a negative 1/4. So 3 over 5/4 or 12/5. So they've given us here that it is centered at 5, and we know we're conditionally convergent at 1, which means our radius of convergence is 4, which means I can go 4 this direction, so 9. So the series converges absolutely at 7. Well, that's between those two, so I think this is absolutely true. Let's check the rest. So is it conditionally convergent at 8? Well, 8 is still before the endpoint, so it's not going to be conditional. It's going to be absolute there, so this is false. It is conditionally convergent at 9. This we're unsure. It could converge conditionally. It could converge absolutely. We're not sure. The series converges absolutely at x equals 10. That is past the radius of convergence, so that's false. So only A is true. Okay, these are looking like what the FRQ should look like. Part A says, use the ratio test to find the radius of convergence is 3. Again, as we discussed earlier, there is no factorials here, so we know that it's going to have a finite radius of convergence, and looking right here at the geometric piece, we can see that the radius of convergence is going to be equal to 3. That works on an FRQ, on a multiple choice, but at FRQ you must show it. So the limit as n goes to infinity of an plus 1 over an. So an plus 1. So we're going to place all of our n's with n plus 1. To times n plus 1 plus 1. Multiply by the reciprocal. Now, as always, we go through and cancel whatever we can cancel. Notice that we have an extra 3 on the bottom. The negative 1 to the n doesn't matter because that means it's alternating and we're inside absolute values. We have an extra x minus 1 on the top. And again, because there's no factorial, we know that the degrees will be equal. Since the degrees are equal, it's the ratio of the leading coefficients. On the top, we have x minus 1. On the bottom, we have 3. This is the ratio test. For this to converge, it needs to be less than 1. So x minus c has got to be less than r. So r is equal to 3. Write the equation of the tangent line of f at x equals 1. So if we want the tangent line, we need a point and a slope. So I'm going to write out the first 2, possibly 3 terms of f. So f of x is approximately equal to, it starts at 0, so negative 1 to the 0 is 0. So we have negative 1 to the 0 is 1. And then over here we got 1 over, now n is 0, so we're going to have 1. And it's going to be times 3 to the negative 1 and x minus 1 to the 0. So the constant term is just going to be 3. Okay, so let's write the next one. The next one is going to be with n is equal to 1. So now if n is equal to 1, we know that's going to be a negative 1 over 3. 3 to the 0 is 0, and then x minus 1. And that's all we really need for this one, because if I want the tangent line, I know my point now is going to be 1, 3. That's my constant. Remember, when you build the Taylor polynomial, the first thing is f of whatever value it was. The next one was the first derivative at that value, and so on and so forth. So now I know my slope right here is in fact going to be negative 1/3, because that's your first derivative. So then your tangent line would be y equals 3 minus 1/3 x minus 1. We can also talk about if this is an over or under approximation by looking at the second derivative. If the second derivative is concave up, we know the tangent line is a under approximation. If the second derivative is negative, we know it's concave down, and the tangent line is an over approximation. Determine if f of x converges absolutely, conditionally, or diverges at x equals negative 2 and 2. So looking at this, we are centered at negative 1, at positive 1. We knew our radius of convergence was 3. So if we go this way, we're going to go to 4. And if we go this way, it's going to be negative 2. We're going 3 each direction. So what it's asking us to do is really find the interval of convergence. So we're going to check the endpoints. So the first one we're going to check is x equals negative 2. We go back to our original function, and we're going to plug negative 2 in for x. So that's going to leave us with negative 1 to the n. And I'm plugging in negative 2, so you're going to have negative 3 to the n, all over 2n plus 1 times 3n minus 1. So looking at this, we can basically see this is going to cancel in absolute value. This right here is harmonic, so we know p is equal to 1. So this will converge if it alternates, but this does not alternate, so this is divergent. So we do not include this, and it's called a divergent series here, so we're not going to include -2. And remember, every time we do these interval of convergence, whatever's the geometric piece here should be canceling that geometric piece up there in absolute value. So we're going to check the other one. So again, check x equals 4. And then we're going to go back to the original series. So you have -1 to the n. This time you're going to have 3 to the n, 2n plus 1, 3 to the n minus 1. Basically, these cancel. Yes, you're going to have an extra 3, but it's not a geometric piece anymore. So we can see this is p equals 1, and in fact, it alternates. So it is a conditional convergence. So it goes all the way up to 4 and including 4. Let g of x equal this integral. Find T3, the Taylor polynomial for g about x equals 1. So the first thing I'm going to do is write the Taylor polynomial for f. We've already kind of got it started right here. So let's go ahead and find the next term. So I'm just going to kind of squish this over so we can see this easier. So this would have been -1/3 x minus 1. The next one would be if n is equal to 2. So it's going to be positive. And if n is equal to 2, down here we are going to have 5. So 1/5 times 3 and x minus 1 squared. So if we want the degree 3 Taylor polynomial, we're going to integrate f. So if we integrate f, that's going to give us g. So this would be 3x minus 1/3 x minus 1 squared over 2 plus x minus 1 cubed over 5 times 3 times 3, and so on and so forth. E. Show that this is true. So this is saying our real value minus our approximate value is less than or equal to this. So this is talking about the error. Now notice this is an alternating series, so we can use the alternating series error bound. So for a convergent alternating series, the error is less than the first omitted term. There's a degree 3 used to approximate. Next term talks about error. Now we don't have that next term, so we're going to have to go and generate it. So first thing, we're going to go generate for n is equal to 3. So if n is equal to 3, it's going to be negative 1/7 times 3 squared x minus 1 cubed. Then when we integrate this, this is now going to be -1 x minus 1 to the 4th, 7 times 3 squared times 4. So now that's our error. So our error is going to be less than or equal to this value. But what did we plug in for x? We plugged in 3/2 for x, so that goes up here. So 3/2 minus 1 is 1/2. 7 times 3 squared times 4. So kind of simplifying this just a little bit because we have to make sure that we actually agree that we think this bound is true, and I just deleted half of it on accident, so let's rewrite it. 1/2 to the 4th all over 7 times 3 squared times 4. So that's going to be 1/2 to the 4th times 9 times 4 times 7. So let's see, it's going to be 1/16 times 9 times 4 times 7. I definitely agree that's less than or equal to 1/3000. So we want to know which one does this converge to. So first thing I'm looking at is that I do have alternating. Sine, all of these alternate, sine, cosine, so I think we're good on there. Now let's see, if it was sine x, it would start with the odds, and it alternates. So checking this one, if I multiplied by x, then I would have x squared, and all of these go up by 1. So that's not true. The next one says, okay, what happens if I replace all the x with x squareds? So that would leave us with x squared minus x squared cubed plus x squared to the 5th, and I believe that's what it is. Which of the following is the power series for sine x squared? So first start with the power series for sine. Those are your odds. And our general term is for the sine is -1 to the n, x to the 2n plus 1, because remember it's the odds, over 2n plus 1 factorial. Now we're going to plug in x squared. So we have an x squared here, there, to the 10th. So this is going to be x squared to the 2n plus 1 all over 2n plus 1 factorial. Here we have a power to a power, so you're going to multiply. So it's going to be 4n plus 2. So it's got to be, let's see, that's not 4n plus 2. This is not 4n plus 2. This one does not alternate, so it has to be that one. Which of the following is the coefficient of x to the 7th for this Taylor polynomial? Okay, so let's build the Taylor polynomial. We'll start with cosine. So cosine x is your evens. Now I never really know how many to go to, so we're just going to try to go, 2 or 3 terms, sometimes 4. Then we're going to multiply it by x. That means everything's going up by 1 power. And now we got 3 minus x cosine x. And we only want to look in front of the x squared, x to the 7th term. Notice if I subtract that, I'm now going to have positive 1 over 6 factorial. So A. Find the interval of convergence. So the first thing I notice here is that it's centered at 3. And all of these are centered at 3. A lot of times you can find it by not looking at where the center is, and the center has to be exactly in the middle of all of those. So that is right now. So the next thing I'm going to look at is the endpoints. So do I think it's 1 and 5 or 2 and 4? Well, you see right here are geometric pieces. I'm expecting my radius of convergence to be 2. In general, this would be x minus 3 to the n over n times 2 to the nth. Do you see right here we have the second power, 2. We've got the third power, 3. We have the fourth power, 4. So looking for those patterns. So I know my radius of convergence is in fact 2. So looking at me centered at 3, I'm going to have to be between 1 and 5. So I'm going to go ahead and check x equals 1, which means we're going to plug it in there. So you're going to have negative 2 to the n times 2 to the n. This is alternating harmonic p equals 1, so this one converges conditionally, and the other one will diverge. We could have also eliminated the interval of convergence being 2 to 4, because if I plugged 2 and 4 in for x, I would not see those geometric pieces cancel. We always have to see these geometric pieces cancel in absolute value. Let h be a function where h has derivatives of all possible orders, and there is a Taylor polynomial centered at -3. Find the first four terms of the series for h. The Lagrange error is less than or equal to k. What is k? So we are using the first four terms for the approximation. So 1, 2, 3, 4. So that's our first four terms. Here we're plugging in x equals -1. So the error has got to be less than maximizing the next term. We went up to degree 3, so we're going to maximize the fourth derivative. And we're plugging in -1, so -1 plus 3 to the fourth, all over 4 factorial. And we know right here, this is the value of the fourth derivative. So it's going to be less than or equal to 5/6 times 2 to the fourth over 4 factorial, which is going to be 5 times 16 times 6 times 4, 24. And then as we start canceling this, we get that this is equal to 5/9. Again, starting with cosine. Cosine's Taylor polynomial is the evens. Its general term. The first thing we're going to do is replace that x with the square root of x. So x to the 1/2 to the fourth would be x squared. And x to the 1/2 times 2n is going to be x to the n. And then we have to integrate this one. And they're just asking us to look at that last term. So it's going to be -1 to the n, x to the n plus 1, all over n plus 1 times 2n quantity factorial. So I believe the answer is D. Well, let me just check D, n plus 1, -1. Oh, nope, that's not right because it's got the 2 in. So it's got to be B. Lots of things to check. You got to check for the alternating, the power on x, the harmonic piece, the factorial piece. And lastly, they want you to build the Taylor polynomial for this. Notice this is as close to geometric as I can possibly think, because geometric looks like a over 1 minus r. We need to make sure there's an r 1 here. So we're going to multiply the top by 1/4 and the bottom by 1/4. So this is -3/4. 1 plus x over 2. So we know our first term is -3/4. So we can get rid of the first two. Our common ratio is -1/2, -x over 2. So that means we're going to alternate, so it's got to be C.